Okay, there we are. Chapter 5, Analysis of Functions and Their Graphs. So, first thing you need to know about how to analyze graphs. Let's say, for example, that I have a function. Oh, there we go. There we go. And it looks something like this. And what kind of graph is that? Good old parabola. Now, what we're going to do first is we're going to look at the way that the graph is bent. This right here, if this was a cup here, Cody, and if I poured water into the cup, then this would hold the water like a well. And so any curve that holds water like this is called concave down. Concave up. So if you have like a cup, that's called concave up. Something that would actually hold water. Okay. All right. If I have a graph, can I erase this one? Okay. If I have a graph also that goes like, goes like this. There's my good old parabola again. And if I was to put water inside of this, it would not hold the water. So the water would fall downwards. It would rain. Wouldn't hold the water. And so when that happens, you have something called concave down. And so the topic that we're going to talk about is called concavity. Concavity is a word that just talks about whether your curve is concave up or concave down. Okay? So we're going to view concavity in terms of whether it holds water or whether it doesn't hold water. Okay? All right, so let's give something a little bit more practical here. We've got a curve that looks like this. Now there is, looking at the curve, you've got several different things going on here. You actually have concave down and concave up in the curve. Okay? Now, can you look at this curve here that I've drawn and can you tell me about where does it stop being concave down and when does it start being concave up? There's a place where that happens. Not a maximum point, because right here, if this is a minimum point, this would be a maximum point. So it's still concave up here, and it's still concave down here. But what I'm getting at is there's a point in here somewhere, Jacob, where it changes. Do you see that? There's a point where it changes from being concave down to concave up. And whenever that happens, whenever you have a place, Tori, a transition point, where it stops being one kind of concavity and changes into another kind of concavity, we call that point an inflection point. An inflection point. So a point of inflection is a point where concavity changes. Now it could be concave down and then become concave up, or it could become concave up and then become concave down. Okay? All right, so let's see if we can find some good examples here. I should have had one ahead of time. I think maybe the book's going to have a nice one here. There we go. Negative x squared minus, that's a parabola. I'm not really concerned about a parabola. I would want a cubic. Oh, they give me a quartic. Here we go. So it's 3x to the fourth, f of x. Can you see the green? 3x to, sure, why not? 4x to the third minus 12x squared plus 2. There we go. All right, let's go ahead and graph this guy. So y equals 3x raised to the fourth power plus 4x raised to the third power minus 12x raised to the second power and then plus 2. So we've got something like this. Zoom out, but I don't think you can see it that well. Okay, do you see that there's a lot of things going on here? Now, this part right here, if I can scroll it, what would we call this portion here? Concave up. That would hold water if I poured water into the well. And then there's a place where it ceases to be concave up. Do you see that this part right here is concave down? Which means that there's some place in here where the point of inflection is. And then this is concave down, right here where the hand is. And then all of a sudden it somewhere becomes concave up again. So the thing that we want to do is we want to find the inflection points. So now we basically have a question that we need to ask. How on earth do I find those inflection points? That is the question, and it's actually pretty easy. Usually. Sometimes. Not all the time. But this is how you do it. What you do is you take what's called the second derivative of the function and you set it equal to 0. And this is the primary way that you find the inflection points. Another way that your calculus book would write that is d2y dx2 equals 0. They mean exactly the same thing. The second derivative is equal to 0.
Can you zoom that graph out so...
I will zoom it out. I don't know if you'll... But that's the graph. Roughly. Very roughly. So what we're going to do here is we're going to find the inflection points. Okay? So let's go ahead and do that. So the function that we're looking at here is 3x to the 4th plus 4x cubed minus 12x squared plus 2. Okay, so let's go ahead and find two derivatives of that. So f prime of x, what's that equal to? Correct. 24x. Now we take the next derivative. Three times 12, 36x squared plus 24x minus 24. Set this equal to 0. Set that equal to 0. Do you see that I have a common factor of 12 everywhere? So I'm just going to divide a 12 out of this. And I'm going to change color because I don't think that green's standing out too well here. So divide by 12 everywhere. So 12 goes into 36 3 times, so 3x squared plus 2x minus 2 equals 0. And what kind of an equation is this? Quadratic. So we can either factor it or use the quadratic formula. I think this one factors. I think this is a 3x and an x, and I could be wrong. I'm now beginning to think I'm wrong. 2 and 1 won't work. 2 and 1 won't work. I'm wrong. That doesn't factor. So if it doesn't factor, what are we left with? Yeah, quadratic formula. So x equals negative 2 plus or minus the square root of 4 minus 3 times negative 2 all over 6, which is negative 2 plus or minus the square root of 10 all over 6. Both of those are real numbers. Both of those are real numbers. And so let's go ahead and figure out where the first one is. Negative 2 minus the square root of 10 divided by 6. So I'm going to open up my calculator here. And eventually it will open when it feels like it. Second, quit. There we go. So negative 2 minus the square root of 10. That comes first. And then divide that by 6. And so what I get, Cody, here, if you can see it, is the first value I get is negative 0.8603791. That appears to be the first inflection point. And so if I go back to the graph, negative 0.86, I'm going to zoom in pretty good here. So here is negative 0.8. So 0.86 is around here. Let's bring this down. Keep going down, down. May have to zoom out a little bit. There we go. There we go. Zoom in. Scroll down, scroll down, scroll down. Here we go. Right about, not perfect by any stretch of the imagination, but right about here, Cody. This is where it's concave up, and then all of a sudden it ceases to be concave up and it transits to concave down. Right about there. Now you really can't see this. I'm going to zoom in on this. My program won't be able to find it perfectly, but do you get the idea? Where it changes concavity? Okay. Where's the next one? Negative 2 plus square root of 10. So what do we get there?
0.1937.
Yes. That's exactly right. So plus square root of 10. I'm going to hit enter. Divided by 6. And so we get 0.1937. And that's your other point of inflection. Okay? So far, so good? So what you tell me, what are points of inflection? Where concavity changes, right. Now, Zach, there are fake points of inflection. Yay! There's fake points of inflection. How would I say this? There are, well, I'm going to just give you a very easy one. This one's not going to be fake, but we need to be careful about how we say this. Let's see. Concave up, concave down. Okay, this one's not fake, but this one's a pretty easy one. What does x cubed look like? Kind of looks like this, right? Okay, so this part right here where my cursor is, if you can see my cursor, we would call that what? Concave down. We would call this part concave up. So from the graph, it looks like the inflection point is where? At 0, 0, 0. So let's just do two derivatives of this. What is f prime of x? 3x squared. And now one more derivative. 6x. Set that bad boy equal to 0. What is x? 0. Yes. Now, here's what I meant by fake. I said I spoke incorrectly, so I'm going to have to fix what I said. It's not that the inflection point is fake. It's that we sometimes use inflection points to find other things right here. Okay? So we look at this right here. This is where 0 is. And so this is concave down, this is concave up. So the inflection point does everything we think it should do. Okay? But sometimes you can use inflection points to find other values. So, for example, does this function here have a maximum value? Is there a maximum value anywhere on this function? There isn't. It's basically infinity, right? It just keeps going up, 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 up. But there's no like a hump or a hill or anything like that there. And vice versa, if I reverse the question, Cody, if I say, is there any minimum? Well, there's nothing that looks like that. Okay? So we have to be careful. We can't just assume that because we set a second derivative equal to 0, then that will immediately imply other things that we want to find about the graph. Okay? We have to have a graph to look at, and then the mathematics is going to hopefully back up the graph. Okay? All right, let's really quickly just talk about increasing versus decreasing. So here's a function. I'm going to say that this point right here is A. And so I want to know on what interval is this increasing? On what interval is this function increasing? And when I say on what interval, what I'm asking is what x values do I plug into the function and get y values that keep going up? So in other words, if I have two x values, x1 is less than x2, two different x values, then increasing would mean this, Jacob. It would mean that f of x1 would be less than f of x2. That's what it means to increase. These are two totally different values, and one is less than the other. Okay? So this is how I figure this out, and this is one way that we can do this. What we can do here is we can color the graph, and does it make sense? I'm going to color this in white. Does it make sense that that's the part that's increasing? So what I do is I cast the shadow of that back down to the x-axis. I cast its shadow back down, and what that gives me, Brian, is that gives me the interval where it's increasing. So the interval is from negative infinity to the point A, whatever the point A is. So when I ask for the interval, what I'm asking for is the x-axis interval. And then maybe you already see it. So what is the interval where this is decreasing? A to infinity. So I highlight the graph with a different color, and I cast its shadow down onto the x-axis, and it's the x-axis interval that I want. So I know that it's decreasing from A to positive infinity. Okay. It's all about the shadow. Now, what does it mean to be decreasing? I know that to increase, x1 has to be less than x2. So decreasing, careful now, still the same. x1 is still less than x2. But what has to be different to be decreasing about the function? F of x1 must be greater than f of x2. Here's a point right here on the graph. So here's x1, and here's another point on the graph. Here's x2. Is the function value here larger than the function value here? Yes. So f of x1 is larger than f of x2, so it's going down. So that's how I know that it's decreasing. Okay? All right. Let's see if we can find a good example to this. Let's see if we can make this a little bit more concrete. Let's go straight to the homework. And I want increasing and decreasing. Trigonometric functions, find the intervals. Intervals, there we go. Okay, let's take, for example, what would be a good one here? let's start with something very basic. So let's start with number 13. 3x to the fourth minus 4x cubed. 3x to the fourth minus 4x cubed.
What was that?
13. Okay. Now, how do I find mathematically how this is increasing? That's the question, and decreasing. So, how do I find mathematically where a function is increasing and decreasing? That's the question that we want to answer. Well, what I do is I look at the very first derivative. The first derivative. Because the first derivative has to do with tangent lines, right? So I'm going to graph this function first. So 3x to the fourth minus 4x cubed looks something like this. Let's erase this. 3x raised to the fourth minus 4x raised to the third. So I get a function, let's zoom out. There we go. So I get something that looks like this, more or less. Now, do you see that this function is both decreasing and increasing? So what I do is I look at the tangent lines. So there's a tangent line here, tangent line, tangent line, tangent line, tangent line. So all of these tangent lines right here indicate that this is decreasing. Tangent line, tangent, 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 until you get to here. Once you get to here, the tangent lines begin to change. Increasing, 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 increasing. So it looks like we found the place where it changes from decreasing to increasing. Somewhere around here, right? So remember, I used the tangent line in order to find this. So what we do is we use the first derivative. Now here's my question, and this is really the key. This is the key. What is the value of the tangent line right here? The slope of that tangent line is 0. Does that make sense to everyone? Jacob, that means that when the first derivative is equal to 0, we have figured out a transition point, not the inflection point, but we figured out the transition point where it could cease to increase and become decreasing, or vice versa. That's the idea. Okay? So what we do is I take that function, which I lovely erased, f of x is equal to 3x to the fourth minus 4x cubed, and I take the first derivative, 12x to the third minus 12x squared, and I set this equal to 0. So what we do is we set f prime of x equal to 0 when we want to find intervals of increase and decrease. So I set this equal to 0. Do you see that I can factor out a 12x squared? So I factor out a 12x squared, and I'm left with x minus 1. Okay? Now what I do is I solve this equation. There's only two solutions, x equals 0, x equals 1. Those are the only two solutions to that equation. Okay? And then what I do is I make a number line. And I'm going to put those points on the number line. And Cody, I don't really care about what the value of the function is on the number line. All I care about is the sign of the value. So what I do is I say, okay, here's my number line. Here's 0 and here's 1. So the number line has been broken up into how many regions here by putting these 2 points? It's been broken up into 1, 2, and 3 regions. So all I do is I plug in a number that's less than 0 first, and I plug it into the derivative, not the original function. I put it into the derivative because the derivative is going to tell me whether it's increasing or decreasing. So what's a number less than 0? -1. So we plug -1 into this function and into the derivative. And so what is f prime of -1? Well, it's 12 times -1 cubed minus 12 times -1 squared. Remember, I don't really care about the number itself. I care more about the sign. So what kind of a number will we get here? Will we get a positive number? Will we get a negative number? Or will we get the number 0? We'll get a negative number, because -1 cubed is a -1 times 12 is a -12. What happens with the square here? It's -1 squared, which is +1, but times a -12. Do you see that I'm going to get -24? But all I care about, Jacob, is that this is negative, which means that the function here is decreasing. Now I plug in a number between 0 and 1. So what's a good number to choose between 0 and 1? 0.5. Somebody plug 0.5 into this. Take your calculator, plug 0.5 into this, and tell me, do you get a positive number, do you get a negative number, or do you get 0? You get a negative number. So, did the function change from decreasing? It didn't. And that's where you have to be careful, Tori. If we plug 0 into the derivative, let me say it this way. 0 is a solution to f prime of x equals 0. It's a solution. But just because it's a solution doesn't always mean, Zach, that the function will stop decreasing and then start increasing afterwards. Do you see what I mean? It could still keep on decreasing. So we have to test it in the number line. All right, now we plug in something greater than 1. So 2, plug 2 into the function. Am I going to get a positive or a negative? A positive. So this is where it starts increasing right here. So now, Brian, I'm ready to write out the interval. So let's look at the number line that we've got. On what interval is the function decreasing? From -infinity to what number is it decreasing? To 1. So it is decreasing on -infinity to 1, and it's increasing from 1 to infinity. Yes?
What happens if, like, you plugged in a number between 0 and 0.5 and you got 0?
Then that would have been a solution to the equation f prime of x equals 0. You would have found it. So because, that's a great, excellent question. Because 0 and 1 are the only solutions in this case to f prime of x equals 0, there are no other numbers where I'll get 0. So it has to be positive or negative. There's no other choice. Yep. Okay, do you see how I use the number line to achieve this? Okay, does that make sense? Any questions? All right, so let's see what we can do right now. Now, I'm going to have you work first with these kinds of functions right here. Let's look at part A. Find the intervals on which f is increasing, the intervals on which f is decreasing, the open intervals on which f is concave up. An open interval is an interval that doesn't have its endpoints. So where is this function concave up? The open intervals where the function is concave down. And can you find me the x-coordinates of all inflection points? Points where the concavity changes. Is that something you feel like you can start to do? Okay. So what I'm going to do, 10 through 24, the evens. That's the homework tonight. 10 through 24, the evens.